All right, this is the second half of the course, biochemistry. And biochemistry is going to deal with carbohydrates, lipids, protein, and nucleic acids. And each one of those segments, we're going to look at first, like for carbohydrates, we're going to look at the monomer. What is the individual unit that makes up a carbohydrate? The individual unit are sugars or saccharides, monosaccharides. So carbohydrates is going to break up into monosaccharides, disaccharides, and then polysaccharides or carbs, the more complex carbs. So here's the main learning goals in chapter 16. Know the difference between mono, di, and polysaccharides. Naming them. How do we name monosaccharides? We look at the kind of functionality that's on it and how many carbons are in it. A key thing to introduce here is going to be stereoisomers or chiral carbons. We'll talk about that. That's why I've got my mirror, not just to comb our hair. Identify monosaccharides as D or L. That's according to their optical isomers. How to draw Fisher projections. Draw and name common monosaccharides using structural formulas. This is where they cyclize. They come on around and form a ring on themselves, the monosaccharide. And that gets into Haworth projections. Benedict's reagent, we talked about that. So that's kind of a quick summary. I've got kits back there. Eventually, in a lot of the biochemistry, you can work in 2s or 4s. I'm going to have you build some molecules so that you can actually, like glucose. Today you'll make a model of glucose. Actually have that in your hand. We'll figure out whether you made the D or the L isomer. We'll cyclize it, how to draw it, that sort of thing. What do we do with carbs? Mostly we burn them. Energy source. This is where you are getting glucose, and the body, 1 gram of a digested carb gives about 4 calories of energy. 4 calories per gram. All right? Don't think that, you obviously can't drive your calories down to 0. You would die. It's taking 1,600 to 1,800 calories a day just to maintain your body temperature. Think about it. The room here is about 20 degrees centigrade. Your body is 38 degrees centigrade. So here you are, you're sitting in a room that's 18 degrees cooler than your body. All right? If your body was doing nothing, it would cool down to room temperature. Doesn't do that. We're warm-blooded. We're 38 degrees centigrade, whether we're in a swimming pool or at the North Pole or sitting in this room. So how does our body do that? It burns calories. And that's producing energy. And it's raising your body temperature up to 98 or 38 degrees centigrade. And sleeping, just sitting there doing nothing, you're burning calories. And in chemistry classes, you're really burning calories. Because your body is pumping glucose into your brain. That's the main place where you're burning your glucose. The more you think, the more energy you're using. You're actually using that energy. Okay, so this is what we do with carbs. It's an energy source. Just a quick example. So there's D-erythrose, D-glucose. And we draw it a particular way. This is how we do draw it. An OH on the right, an OH on the left, and another OH on the right. We'll see why in a little bit. General formula is CH2ON. So this has got, N here is 6. 1, 2, 3, 4, 5, 6. What does the N stand for? How many carbons are in the sugar? And glucose is C6, H12O6. It's following that formula. So it's CH2O6. You get C6H12O6. Multiply all those by 6. That's glucose. Remember when we were studying aldehydes, we said, let's say I had an aldehyde like this, 6 carbons long, and these were all hydrogens. I said, well, and those of you in the 1107 lab, you did some of this. This is hexanal, and hexanal was not soluble in water. Hexanal is not soluble in water. Why? This is all non-polar bonds right here. Carbon, 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 hydrogen, relatively non-polar bonds. Now all of a sudden you get glucose in here, and this bottom CH2, you got an H, you got an H, you got an OH, polar. A water molecule can come along here and hydrogen bond right to that OH. Hydrogen bond to that OH, that OH, that OH, that OH. Every single carbon is got a polar group on it. And glucose is very soluble in water. Pretty smart of your body to burn glucose and not to burn hexanal, because how does your brain get the glucose? In blood plasma. Yes? Oh, I need another carbon. 1, 2, 3, 4, 5. Sorry. 6. Thank you. Details, details, details. Of course, I hold you to details, don't I? Probably thought, he doesn't even miss a hydrogen. Oh well. It'll be over by next Friday, okay? You can go back and be casual, but until Friday you can't. Trying to make nurses out of you that pay attention to details, right? Not a bad trait for a nurse? No. Okay, you get plenty of it here.
Is that supposed to be HOCH? Are they supposed to be on the same side, or is that supposed to be on the other side? Like you see 1, 2, 3 carbons down on the glucose?
This here?
Yeah.
Yeah, those are OH. Those are hydroxyl groups.
Yeah, but then it flips to the other side, so is it supposed to be like that?
Yeah.
Okay.
Yeah, because it is. You're talking about this one?
Yeah.
So it is bound to the oxygen. All right? So if I come down here, I write it like that. Okay? So I flip the... I have the carbon attached to the oxygen. Here I have the carbon attached to the oxygen. No matter which side of the carbon it's on, it's always attaching. Now at the top, we write it like that because the hydrogen, this hydrogen is, oh yeah, that comes down. There we go. Good. This hydrogen is not attached to that carbon, but that hydrogen is. You see at the top with the aldehyde?
So it still has the free range.
It can, yeah, it can rotate around up there, yeah. Okay, so sometimes monosaccharides will be indicated this way. This is taking the glucose in a chain and cyclizing it. It will form a ring. We'll get into that in a minute. So you'll see monosaccharides kind of represented this way. There is an oxygen right here, so that's a little bit misleading. That's not a cyclohexane. it's 5 carbons and an oxygen that's in the ring for a monosaccharide. Here is a disaccharide, so 2 monosaccharides attached to each other. Disaccharide. Okay, I want to introduce you to a new prefix here, oligo. Oligo is kind of between a disaccharide. It'll be used even with proteins and other things. An oligomer is between 2, 1 or 2, and many. So we would use oligo when there's 3 to 10 units. We would say it's an oligosaccharide. And actually this is coming up in news articles that you see. Yes?
Can you repeat again? You use that when what?
When there are somewhere between 3 and 10 units, you would use oligo. And then kind of when it gets over 10, it's a poly, or many. Many. Yeah, in the language, we would say, how many people were there? There were 2. Or there was a pair, or there were 2 people. How many were there? Several. We'd say, how many people were there? Many, okay? So we're going from di is 2 to a few would be oligo to poly for many. Polynesia is a country of many islands. I forget, over 1,000 islands. Polynesia, a lot of islands. Okay, so this would be a homopolysaccharide. We're depicting here, for example, if those were all glucose sugars there, it would be a homopolysaccharide. This would be a heteropolysaccharide. And here would be a branched one. So it's not only got different sugars on it, occasionally there's a branch. This is a particular link between one sugar to the other normally, but on occasion there'll be a chain coming off of it. So that's a branched. Okay, naming monosaccharides. Like I said, what we're going to look at is how many carbons are in it, and where is there's going to be 1 carbonyl on every monosaccharide, just 1. And the rest is going to have OH groups. But that carbonyl can either be an aldehyde, like this, and like this, or it can be a ketone, like this. So if it is an aldehyde, we're going to say it belongs to the category of aldoses. Aldose. So both of these are aldoses. This is not an aldose. This is a ketose, coming off the fact that it's got a ketone carbonyl. Number of carbons, 3 carbons. It's a triose. So this is a triose. 6 carbons, this is a hexose. This is 6 carbons, so that is also a hexose. So what differs here? This is an aldohexose. It's an aldehyde functional 6 carbon saccharide. This is a ketohexose, a ketone functional 6 carbon saccharide. All of these terms right here, these terms out here in purple or black or whatever color that is, are basically just categorizing the saccharide, not naming it. Saying what category is it in? Like you are an NVC student, all right? That's one category you're in. But that's not your name. It's not your name. The name of this molecule is glyceraldehyde. name of this molecule is glucose, and the name of this molecule is fructose.
So what did you say an aldose was again? One carbon?
No, an aldose is an aldehyde functional saccharide. Doesn't tell you how many carbons. Aldose just tells you it has an aldehyde functional group at the top. One other thing to keep in mind, we're going to have to kind of come up with a common way of drawing these molecules. One commonality in there is always to draw the molecule with the carbonyl towards the top. For an aldehyde, it is at the top. That's carbon number 1, 2, 3. 1, 2, 3, 4, 5, 6. The aldehyde is at the top. Here is the carbonyl here in fructose. We're gonna put that up towards the top. This is carbon number 1, 2, 3, 4, 5, 6. And what you will find, even when it is a ketone, it's usually on the second carbon. I'm not sure of an exception to that. I don't know of an exception to that. So the carbonyl is always either right at the top or in position number 2. Okay, so there's a number of things we're going to have to do in a certain prescribed way in order to draw these correctly, so that someone wouldn't get, so we would never draw glyceraldehyde upside down. You know, we're not going to draw it like this. I say never. The only time we would do that is to show you what a bad example that would be. All right? So we're not going to turn it upside down. We're going to flip it up that way all the time. And you can see towards the bottom, you're usually ending up with a CH2OH group. So really at the bottom, so that's what that looks like. That's a CH2OH. I don't know where the OS comes from, but usually OSE is going to point you towards a carbohydrate, whether it be a mono or a di. You won't. Sucrose is a disaccharide, sucrose. Glucose is a monosaccharide, so they're both saccharides, but they both end in OSE. So you can't tell whether it's a mono or a disaccharide. You're going to have to memorize a few disaccharides. Just know that they're disaccharides. Praying hands. Time to say our prayers. We're getting into optical isomers. Why is this here? What this is pointing out to you, your left hand and your right hand are not identical. They're not identical. They are mirror images of each other. If they were identical, I could superimpose. I could take my right hand and superimpose it on top of my left hand. It is, I don't know, my left hand, the mirror image of my left hand is identical to my right hand. Can you see that, Caitlin? Okay? See that? The mirror image of my left hand is identical to my right hand. But that's the mirror image. So this is the mirror image of this. Left hand, right hand are mirror images of each other. I'm going to have to switch over here. It's going to have to be my right hand is the mirror image of my left hand. Okay? I need a couple little molecules. Okay. All right, this is a riddle, a game, a quiz, a test, a challenge. Call it whatever you want. Are these the same? You're not even that worried. We just got a carbon here. Now remember, a carbon will form 4 bonds. So we got 4 things on this carbon. They're all different. I mean, you could say that's a oxygen, that's a nitrogen, that's chlorine, and that's hydrogen. Whatever you want to say they are, doesn't matter. They're different. 4 different things on that carbon. 4 different things on this carbon. Same thing. Oxygen, nitrogen, chlorine, hydrogen. They're the same. Are they exactly the same? Yes. They look like it. They deceptively look exactly the same. Now, what would be the test to answer that question? Are they exactly the same? What would I do? Not chemically, but just physically, what would I do to prove that this is exactly like this? Well, break them apart. If I broke them apart, I would have a carbon, they would be exactly the same. I would have 5 things, and those 5 things are the same in both of these molecules.
Molecular weight.
Try to look at them from the same angle.
Like with the green on top and then place both whites forward.
Okay.
Place both whites.
Well, both white, green on top,
Yeah.
and both whites forward. Okay, let's do that.
Oh no, they're image of each other. Yeah. So one's red and blue and another one's red.
So what we could do that, exactly what you just said, or we could say, okay, let's take this molecule and set it on top. So I'm going to put the blue, you could do it any way I want to, but I'm going to put the blue on the blue, the red on the red, and see if the white is on the white. It isn't. See if the green is on the green. It isn't. So these molecules are not superimposable upon one another, which means they are mirror images of one another. They are a special kind of isomer. They're optical isomers or stereo isomers. We've got 2 molecules here in stereo. Like perfect left-right music coming in. So let's see here. So let's do what Desiree was saying. We got the white. You had the green on the top, the white coming towards you. And let's put the green on the top and the white coming towards the mirror. I can't see this, okay? I can only show it. Does this look identical to that? Does the mirror image of this look just like this? Okay, so they are mirror images of one another. It's you can see here. All right, there. If you look at the image of this in the mirror, it is exactly what you're seeing here. And if we put these right next to each other like this, okay. All right, you put these right. Imagine a mirror right there. You see that they're the reflection of one another, like the hands are reflections of one another. They're mirror images. Okay. Now I make a big deal out of this because, I mean, when you first looked at these and you say, they look the same. If we had chemicals like this and took them in the laboratory, they would react the same. There'd be no difference in the way they reacted. But you take glucose and the mirror image of glucose, and your body will metabolize the one and discard the other one. They're chemically identical. How do they do that? Well, the body doesn't just do wet chemistry like we would do at a lab bench, just mix things together. The body does chemical reactions with protein molecules, extremely complex protein molecules, and this thing could kind of come on into a protein, and it doesn't like this one because it says, hey, I only work on this molecule when the oxygen is over there. And so it only works on this isomer. And it doesn't even let this isomer come into the protein to react. And you're going to find this in nature. The trees out there are making glucose. Sun's shining down in there. They're taking carbon dioxide and water and converting it into glucose. D-glucose, a particular isomer of glucose. 100% of the time. And that's what's getting into the food chain, is D-glucose. And the proteins in your body will handle the D isomer and discard the L isomer, or the L isomer will cause your body problems because it messes things up. All right, so this is what gives rise to these prefixes in front of the name. Okay, I'll tell you what. While you guys make your glucose, I'm gonna put together this glyceraldehyde, and we'll talk a little bit more about these isomers. Let's go back to this. Work in as big a group as you want, no more than 4. But don't work on your own. 3 or 4 of you. Go get a kit back there. And what you want is carbon is going to be the black. Oxygen is red. Hydrogen is white. And make this molecule. 6 carbons, and we'll use it. So we'll make it and we'll keep it. We'll probably keep it around for a day or 2. Because after you make it, we're going to figure out whether you made the D or the L. And this would be a good time to take a break. Make your molecule, take a break. Get your chapter 15 homework up here.
I think you're just making the middle one. We're just making the middle one, right?
Yeah, just make the middle one. Now, remember, folks, on that carbon-oxygen double bond, use flexibles and make a carbon-oxygen double bond like that. That's what your aldehyde should look like at the top.
Wait, it's not me. I know, sorry, I thought you were. Got started. No.
Do you have oh, give me another oxygen, please. What do I need? Two oxygens. Will you have enough?
We'll see.
No, you might run out. Yeah, there you go. Good. Yeah. Alejandra, did you know there are roosters on campus?
No, I don't know.
Yeah, there are 2 roosters. Do you need any roosters?
Yes. I'll take
Go
them.
catch them. I don't know what they would think, but I think they just wandered onto campus. Yeah, they're back there. You know where the bridge is? Where the walk bridge behind our building?
No, I haven't gone.
Okay, you haven't. Well, if you go out the back side of the building and go across that bridge, which goes across the stream, and they're back in there. I come in the morning and they cock-a-doodle-doo, and they just showed up about a month ago. They were wandering around in the parking lot back there in the trees. 2 roosters.
I have a trap, but I don't know if I could put it.
Why, do you need a rooster?
Well, I have 4 chickens and 1 rooster. But my 3 chickens, I don't know why, because they're like territorial. They don't like this particular chicken, so she's always by herself.
The rooster?
1 chicken.
1 chicken.
Because the 3 other chickens will fight with this 1 chicken. So she's always by herself. Like, they have like a little and the
Click.
other one is always by herself.
Huh.
So it'll be good for her. She'll have somebody, you know?
A rooster.
Yes, at least, but I have to catch her. Yeah, she's always by herself, the poor thing. But the roosters, they protect the chickens.
They do.
Yeah, even from me.
Even from you.
If I try to catch him, he will go after me. But that's a good thing, because they're supposed to do that.
Okay.
And then
Okay. They're pretty. They're pretty roosters.
I need to look for them.
Well, walk out the back, go out the back, and walk across the bridge. I haven't. You can't just look out there and see them all the time. But in the morning, they're.
They're there. But I have a trap. Maybe that will let me put my trap there.
Yeah,
I'll take a-
park in the back there.
I'll look for them. Thank you so much.
Yeah.
See, this one has milk. This one has 6. So maybe, yeah, right? So 3 is. And now we put all the height. This one needs a. So no, we need more oxygen. We need an oxygen.